Okay, so now let's talk a little bit about properties of convergent series. We kind of already have used this with our telescoping. This is just general, lay it out for you. Is kind of what's going on here. So suppose I have some series that converges to A and C is a real number. I can take this C and pull it out in front of my series. So I can just take C, some constant value, and then multiply it by A. These are really just all the same stuff that we already know. You can pull out a constant in front, right? What's the basis of an integral? Is a summation, right? So that's all that's happening here. I'm doing these summations, and I can pull this constant out in front. We can do that with limits. All of the same criteria happens. If this diverges, then if I multiply it by a constant, that still diverges, right? If I have these two values that converge, I can now add or subtract those together. Okay, right? We kind of did that already when we did our telescoping. We were taking the sum of each one and we can add and subtract those. It's the same concept that's going on. If one of them diverges, now here's this. If one of them diverges, then the whole thing diverges, whether you're adding or subtracting. That makes an impact. So even if one converges, it doesn't matter. If one of them that I'm adding and subtracting and putting together diverges, then the whole thing diverges. It's kind of like when we take our limits, right? If one of them goes to infinity, then the whole thing does. It's the same deal. Here, I can move this. Whatever this value is, I can then take and manipulate it a little bit if I need to. Regardless of what happens here, they're either going to both converge or diverge at that point. All right, so, or not at that specific point, but just in general. They're either going to both converge or diverge. Because sometimes you can manipulate your series. Let's say that this was k plus 2 or something, and I wanted to subtract 2 from everything. I can subtract 2 from my series. You're still going to end up with the same thing. You can just manipulate it a little bit. Kind of like how we got fancy with our integration manipulation. You can get fancy with these manipulations sometimes if you need to. In general, convergence does not depend on a finite number of terms. This is going to infinity, right? So if I want to start at something to make it easier, then that does make a difference. However, this is a good point. The value of the convergence series does change if non-zero terms are added. So if you have a geometric or a telescoping, if you start messing around with this, then that does make an impact if you mess around with it too much. Determining convergence or divergence, it doesn't matter. But if I want to come up with an actual value, then that's going to make an impact. So you can't just horse around with it too much. All right, let's try some. So using these properties, which basically is stuff we already know, then we can come up. I've got two examples for you here. So here's example 4. We're going to evaluate the following infinite series. And I have k going from 2 to infinity of 1 over 3 to the k minus 2 over 3 to the k plus 2. All right, so I have some adding and subtracting going on here. You can look at this in terms of a telescoping series and figure that out because I've got that subtraction. That subtraction with those two fractions. But what else do you notice is going on here? You've got that geometric, right? You've got that to that k exponent. And we can work that out. Now, what do you know about this one over here? Let's take a little sidebar. If I have this 2 over 3 to the k plus 2, when you have like bases, you add those exponents. This is the same thing as 2 over 3 to the k times 3 squared. Do you see that? Like bases, you add the exponents. So you can break that up to have these like bases. Now you have this constant times 1 over 3 to the k. Because that 1's in the numerator, 1 to any power is still 1. And you've got that 3 to the k. So what you can actually take this sidebar do, oh my, is look at this and see that you've got a couple of geometric jobbers going on here. And then that's 3 squared, so I'm going to write 9, just because we know we already have that on there. Do you see that? And I can look at these as geometric and geometric. Now my question here is the fact that what is my R value, right? So in this instance here, R is equal to 1/3, which is less than 1. R is equal to 1/3, which is less than 1. Now, something I don't think I said on the geometric, but you need to know, anytime you have geometric, you have to have this step. Because that proves, can I even proceed, right? So you have to determine your R value to determine if you can proceed or what it is that you have going for you here. All right. Now, notice, what am I starting my geometric series with? Ooh, remember what that does to us? So my A value is going to be 1/3 squared for that one. And my A value is going to be 2/9 times 1/3 squared for this one. So I'm adding and subtracting these two geometric series. So for this first geometric series, if you have A over 1 minus R, my A value is 1/3 squared over 1 minus this 1/3. And then I'm subtracting. My A value here is 2/9 1/3 squared over 1 minus this 1/3. Now, do work. So I am going to simplify this, get your common denominators. And so this is the same thing as 3 over 3. So I really have a 1 squared over 3 squared, right, for my numerator. And then my denominator here is 2/3. So I'm going to multiply that by a 3/2. One of these 3's cancels out one of those 3's. And I'm left with a 1/6 minus 2/9 times 1 over this 3 squared. When I multiply by the reciprocal, the same thing as I get 2/3 in the denominator. So multiply that by a 3/2. This 2 cancels out that 2. This 3 cancels out one of those 3's. And I'm left with 1 over 9 times 3 is 27. Do you see that? So it's just doing that, the number sense, and you multiply that out. So now I have 1/6 and 1/27. Now what in the dickens is that common denominator? This is 3 cubed, so I need to take that times 54 would be my common, right? And this is what my head just did. If I'm looking at this, here I have a 3 and a 2. Here I have 3 cubed. So if I have 3 cubed here, I'm missing this 2, so I need to multiply this by 2. Here I have a 3 times 2, and so then I need to have 2 more 3's over here, because this is 3 cubed and I only have 1 3. So I need to multiply this by 9 over 9. And that will give me 9 over 54 minus 2 over 54, the grand total of 7 over 54. So my final answer here would be 7 over that 54. All right. I don't believe I can reduce that, so we should be good. Very good. Okay, let's do the next one. And I have this. I've already lost my place. Here is example 4b, and we end up with k is going from 1 to infinity of 5 times a 2/3 to the k minus 7 to the k minus 1 over 6 to the k. All right. Again, we got a couple of geometric going for us here, right? Geometric. And this one is also a geometric, but let's pull this out and see what this looks like. Same thing, like bases, you add the exponents. This is the same thing as saying 7 to the k times 7 to the negative 1 over 6 to the k, right? That 7 to the negative 1 just comes out in front, so I get 1/7 because this goes to the denominator times 7 over 6 to the k. Now, time out here. What would my r value be for this problem? 7/6. What do we know? That is greater than 1. So then that one diverges. If one of these diverge, then what do we know about all of it? Yes, the whole thing diverges, so be smart about that. This one obviously converges. We could do all of our work and come up with it, right? Because this 2/3 is less than 1, and we could do something with that. But the whole point is this one diverges, and my tip-off was this 7 is greater than 6. So I wanted to look at that a little bit closer to see what we have going for us. Therefore, the series diverges. I don't have to do any more work. There's nothing else that can be done. That just diverges. All right?